In the last class, we were dealing with this problem here that talks about a survey of 2,032 young people, ages 8 to 18, and asking them how many of them had a television in their room. And 68% of them answered yes. So this 2032 is a sample of American youth ages 8 to 18. So our N, we can see from this, just the description here, is going to equal 2032. So the observational units, I would say, are the 2,032 youths that were surveyed. The variable is whether they have a TV, yes or no. So it's a categorical binary variable. And since it is a categorical variable, then the parameter of interest is a proportion. So remember, categorical variables deal with proportions. Quantitative variables will end up dealing with means. Okay, but we're dealing with a proportion this time. So the 0.68 is a statistic because it comes from the sample. So we're going to say p hat equals 0.68. And what we're trying to do is we're trying to find, well, the relevant population parameter of interest that we are looking for is we would like to know what pi is for the entire population of American youth, ages 8 to 18. So again, we're going through our, we start with the population. From the population, we take a sample. From the sample, we gather statistics. And if we've done everything right, from the statistics, we can infer, predict, project a parameter. So this survey is it going to allow us to determine the exact value of the parameter? No, it's not. Because to do that, we'd have to survey all American youth ages 8 to 18. And by the time we finished, a bunch of them, their televisions would have broken. So we're using a statistic from samples to try and infer the parameter. So can we use the central limit theorem? Well, the test that we need is n times 1 minus pi greater than 10, or n times pi greater than 10, but we don't know pi yet. So that's going to cause us a little bit of a problem. Not much of a problem, but a little bit of a problem. What we are going to do is we are going to use p hat as a substitute for pi to enable us to follow our process of making the sketch and determining what the standard deviation, although we're going to give it a new name, what the standard deviation is, and then being able to use our normal model rules and our TI calculators to calculate some probabilities. But the key thing here is that we don't know what pi is. We'll actually never know what pi is. We'll never know the exact population parameter. But we will know p hat, and we can use p hat very effectively. So this should look very familiar to you because we're very familiar from last chapter on the central limit theorem with how to calculate the standard deviation of a population if we know pi. We don't know pi, so what we do, instead of calling it the standard deviation, we call it the standard error. Standard error right here. I don't know why they call it error, because it's not really an error. It's just how far away you are from the mean. And when we write it like this, standard error SE of p hat. And you'll notice that this looks very similar to that. Instead of pi, we're using our p hat. So let's calculate the standard error for the survey that we were doing. Our p hat was equal to 0.68. Our n, the sample size, was 2032. So I'm going to go 0.68 times 1 minus 0.68 divided by 2032, and I'm going to take the square root of that. This, as you can see, is p hat times 1 minus p hat over n and the square root. That is going to give us our standard error, which is just like the standard deviation based on p hat. So 0.68 times 1 minus 0.68. Let's divide that by 2032, our sample size. Let's take the square root. And we find our standard error is approximately, let's call it 0.1. Well, I'm not going to do this right now. I'm going to draw my picture. So what I know is that p hat is equal to 0.68. I know that the standard error of p hat is equal to 0.01. I know that my n is equal to 2032. So I'm going to test whether the central limit theorem will apply. And since I'm substituting p hat for pi, I'm going to go n times p hat. Is that greater than 10? And is n times 1 minus p hat greater than 10? Well, I can tell right off that 0.68 times 2032 is greater than 10. And 0.32, which is 1 minus p hat, is equal to times 2032, about a third of it is greater than 10. So my conditions for the central limit theorem they apply. So I know that my shape is going to be unimodal and symmetric. And I know that my center is going to be p hat, which is 0.68. And I calculated my standard error, which is 0.01. So I'm going to make my -3, -2, -1, 1, 2, 3 standard deviations, although now they're called standard errors. And I can see that this is going to be 0.69, 0.70, 0.71, 0.67, 0.66, and 0.65. So now I have a nice diagram. Well, what can I do with this diagram? This is all based on my sample, where I got a p hat of 0.68. Well, I have a normal shape, and I know the empirical rule. So I know that 68% of the data, or approximately 68% of the data, is going to go between the first two, the standard deviation -1 to 1. 95% of the data is going between -2 and 2, so 2 standard deviations from the mean. And 99.7% of the data is within 3 standard deviations of the mean. So I'm going to introduce an important term here, and that is a confidence interval. Even though this is based on p hat, on the results of a sample, I can say, for example, I am 95% confident, right here, 95% confident that the actual value of pi, the population proportion, falls in the interval 0.66 0.70. That is an astounding thing to be able to do, to predict, to infer the population proportion, which I'd never be able to actually know for sure, but I can say it is between 0.66 and 0.70. Between 66% and 70% of all American youth have a television in their bedroom, at least at the time of this particular survey. So you can see that a confidence interval is a very, very powerful tool to use in inferential statistics. Well, it's just wonderful if I want a 68% confidence or 95% confidence or a 99.7% confidence interval. But what happens if the confidence that I'm seeking isn't exactly one of these nice numbers for our based on our empirical rule? What if I wanted to have, say, an 80% confidence level? Okay, now I want to be, I'm saying less confident than 95%, but more confident than 68%. So an 80% confidence level is going to be somewhere kind of in here, between 1 and 2 standard deviations away from the mean. This is going to be 80%. I want to know that my value of pi, I want to be 80% confident that my value of pi is between two values, and I don't know what those values are, so I have to figure them out. It's important to remember that these numbers here, -3, -2, -1, 1, 2, and 3, those numbers there are z-scores. A z-score is how many standard deviations away from the mean I am. And those numbers that I just circled, which I'm now going to uncircle, those just happen to be integer z-scores. But we know from our past work that there's z-scores all over the place. You know, any spot can have a z-score. But how am I going to find the z-score for, say, this point right here? Well, I know that I want to be 80% confident. So this distance between here and here is 80%. And since my normal model is unimodal and symmetric, I know that the left side of it is 40%. The left side of the mean of p hat is 40%. And the right side of the mean is 40%. So the way I look at it is this. I start over here, which is 0% of the data, and I'm heading over to here, which is 100% of the data. I know that from 0 to the middle here, to my p hat, is 50% of the data. And since I know that my 80 confidence level that I want is divided into 40 and 40, I know that from the middle over to here is an additional 40% of the data. So this bar right here has a percentile, percentile, is the 90th percentile. I start over here from 0, I get to 50, I add 40. This line is the 90th percentile. And if we remember, when we use the function inverse norm on our calculator, we enter in the percentile and it gives us the z-score. So let's do it. I'm going to go second distribution, inverse norm, 0.9 for the 90th percentile. It's not the 80th percentile. 80 is in the middle here. It's the 90th percentile, so 0.9. And I find out that that z-score is 1.28. Oh, let's call it 1.282. That is that z-score. So if I want to find the value, the proportion that is represented right at this spot, well, all I need to do is I need to take my p hat, my center, and add to it 1.282, the z-score, times the standard error. In other words, I want to go, if it was an integer, then I would just use, one standard deviation or one standard error, which was 0.1, or two standard errors, that would be 0.02. But since it's an in-between the z-score, I'm going to multiply it times what the z-score is. So I'm going to take 0.68 plus 1.282 times my standard error of 0.01. And I'm going to find out 0.68 plus 1.282 times 0.01. Be careful of your order of operations. And I find out that this value right here is 0.69282. Now, the model is unimodal and symmetric. So that means that if this is positive 1.282, this is negative 1.282. So I can actually write my formula here as p plus 1.282 times the standard error, or p minus 1.282 times the standard error. So p hat plus or minus 1.282 this times the standard deviation. So to find the other side, 0.68 minus 1.282, the number of z-scores, the number of standard deviations away from the mean, times what the standard deviation is, and that gives me 0.68 minus 1.282 times 0.01. This one right here is 0.66718. So my confidence interval is 0.66718 or comma 0.69282. I am 80% confident that the population proportion of pi lies between 0.66718 and 0.69282. This formula here, p hat plus or minus the z-score times the standard error, and this z-score right here has a special name. It is called the critical value, and it is symbolized by a z asterisk. So there is kind of another way that we could have arrived at these numbers of 0.66718 and 0.6982, and that is we could have used the old standby z equals x minus x bar over s. So I could have said, I know my z-score was 1.282 is equal to, well, I'm looking for the x, minus 0.68 divided by the standard deviation, or in this case, the standard error. So I could multiply s on both sides, and I get s times 1.282 equals x minus 0.68. And I add 0.68 to both sides, and I have 0.68 plus 1.282 times the standard error. Well, doesn't that look like the same thing as p hat plus the z asterisk times the standard error. And since it, I mean, it does, it looks exactly the same. So and that would get me one side, and then the other side we know has a z-score of negative 1.282. So if I did that with this being a negative, it would just make this plus or minus. So you can kind of look at it using our old standby formula, or you can kind of remember that it's p hat plus or minus the critical value times the standard error. It's actually good to kind of study this and think about it and understand the relationship between these two. Because if you understand the relationship, then you're not going to have to memorize it and fill your head up with a bunch of clutter. By understanding it, and particularly by understanding how it relates to the picture, that's what's really going to help you. Because the picture and figuring out how do I find this z-score over here and then turn that z-score into an actual proportion number, that is really what's going to be the key to you understanding how this process works. Well, I really encourage you to study the diagram and kind of struggle to understand how this works. I have listed like a step-by-step method for how to do this. It might help you to follow it the first few times, but always do this using a picture. If you do it using the picture, it's going to really emphasize to you how this thing is supposed to work. But I thought I would give these steps to you anyways.